So let's do an example of a collision in two dimensions and how we would use momentum and energy to and forces to kind of solve this kind of problem. So we have one car of mass 1 that's equal to 900 kilograms, and it's traveling in a traffic circle with another automobile of mass M2 equals 1200 kilograms, and they collide. And just before this collision, mass 1, car number 1, was moving due east. So we're going to give that a velocity that's traveling due east. That's going to be in the right direction. And then we have the other car that's moving at 40 degrees south of east. So we can plug this in. We have this other car that's moving south of east. So I draw in my east vector, and I'm going to be going south of east. That's some angle theta, and that angle theta is going to be 40 degrees. After the collision, the two cars are going to remain entangled while they skid with locked wheels until they come to rest. So that's what we see down here. My two cars collide, so my total mass is going to be mass 1, 2, which I'm calling mass 1 plus mass 2. And we can go ahead and we can add those up so that we know that mass 1, 2 is equal to 2100 kilograms. They're going to have some initial velocity, v12, that's going to be created from the momentum that they get when they collide right here. And they're going to skid off in this kind of general direction, kind of down and a little bit to the southeast. And they're going to come to a stop, so they're going to come to a rest. So v12 final is going to have to be 0. We know that the speed of the first car before the collision, v10, is 14 meters per second. And I'm tacking on this little I hat to represent that velocity is entirely in the east direction. I know other things. I know that these skid marks, so the skid marks, the distance that this travels, is going to be equal to 17.4 meters. So the change in position of these cars when they skid is 17.4 meters. And I know that the coefficient of kinetic friction between the tires and the pavement, this mu, is going to be 0.85. I am supposed to calculate the speed of the other car before the collision. So I want to know how fast this car was going. This would be a very good situation, a very normal kind of situation if, say, I'm a police officer and I need to measure some things that happen and figure out if one of these cars was maybe speeding and broke the law. So, how do I approach this problem? Well, first, I've already written down everything that we know. I've written down all the initial conditions, everything that's happening in the beginning, and everything that happens at the end. And what I can see is in my initial conditions, I have something moving at an angle. At any time I have anything moving at an angle, we've done this many times before, we separate it into the x and y components. So let's draw in those components. We've got some bit in the x direction, and we'll call that v20x. And we have some bit in the y direction, some bit that's going down. We'll call that v20y. Okay. And I can actually write out what these are. I can write out v20x in terms of v20, which is what I'm looking for. So v20x is v20 times the cosine of my angle, and I'm given that my angle is 40 degrees. I know that. I'm given that angle in the problem. Then I can also write down v20y. That's going to be equal to v20 times sine of 40. And this is kind of everything that I know about this problem. I have tons and tons of information, so now let's get to actually solving some things. And what I want to do is think about what kind of view I have right now. I have an overhead view. And what I want to do is get a kind of different perspective. I want to get a kind of sideways view. So instead of looking overhead, we're going to change our kind of perspective and kind of look from the side at this situation where I have this car combined together. These cars crash and they skid to a halt. They skid some distance, and we know this kinetic friction. We know this final velocity. So we know a whole lot of information about this final situation. So we're going to see if we can use that to get even more information for helping us to find our v20. So here's what we have in a sideways view. We have our cars that have collided, and our big collision starts at some initial velocity v120 that it gets from the momentum of that collision beforehand. And it kind of skids, and these cars skid and move some distance, 17.4 meters, and they have a final velocity equal to 0. And we know that friction is causing these things to slow down, and friction has a coefficient of friction of 0.85. So I see this friction right here, and I think that's going to involve forces. So I need to start thinking about the forces that are acting on this car. We have several forces. We can identify the force of gravity acting straight down. We can identify the normal force acting straight up, perpendicular to the surface that the cars are skidding along. And we have the force of friction acting backwards to slow my car down. And like we've done with all of our force problems in the past, we want to take this and we want to start solving some things. We want to separate things into the x direction and the y direction. So in the x direction, I can write my sum of forces equals the negative force of friction, because friction is acting backwards. And that's going to be equal to the mass times mass 1, 2, which is the mass of the combined cars, times the total acceleration that these cars would have. And now I can see right away, I'm going to start getting some useful information. I can find this A. So if I rewrite this information that I do know already, kind of my delta x is 17.4 meters. And this is a little chart that we've been doing since basically the first or second week of class. V12 initial, we don't know what that is. We know V12 final is equal to 0. If I can find the acceleration, then I can find V120. And if I can find V120, maybe I can back that up into finding some things in the before the collision. So I can solve this equation that I have in the x direction. This force of friction, negative force of friction, equals mass 1, 2 times A. So I can plug in what the negative force of friction is. Force of friction is negative mu times the normal force, which is equal to mass 1, 2 times A. And I can solve this through for A. A is equal to negative mu times the normal force divided by mass 1, 2. I know what mu is. I'm given that. I know what m12 is. I can calculate that by adding together the two masses. So now I need to know what Fn is. And in all the previous problems we've done, we can find Fn by going to the y direction. So we have the sum of forces in the y direction. It's going to be equal to any force that's going up, which is going to be the normal force, minus the forces going down, which is the force of gravity. And this thing isn't accelerating in the either direction, in the y direction rather, and we get 0. So we know that the normal force is equal to Fg. So the normal force has to be equal to mg, m12 times g. And I can take this and I can plug it in for my normal force. So I get A is equal to negative mu times m12 times g, all divided by m12. I notice my m12's cancel because I have them on the top and on the bottom. So my acceleration is negative mu times g. Negative mu times g, which is just going to be a number. And I can calculate that number. A is equal to negative 0.85 times g, which is 9.8. And I find that A is equal to negative 8.33 meters per second squared. So I did all this from a side view by using the forces and by using just some basic reasoning to find out what this A is. And this lets me fill in my chart so that I know the change in position. I don't know V12, but I can find it because I knew V12F and I know my acceleration. So let's do that next. So all I've done here is rewritten the same information that I just found, that I just solved for, and I've written one of the kinematic equations. And I selected this kinematic equation because it had all the variables that I was currently looking for and that I actually already had numbers for. So I can plug and chug my numbers in. And what I'm looking for, I'm looking to find v120. So let's get that by itself. So to get that by itself, I need to subtract negative 2a delta x from both sides, minus 2a delta x. So that'll cancel on the right-hand side and give me v12f squared minus 2a times delta x equals v120 squared, and I can take the square root of both sides, and that'll give me v120 equals the square root of v12f squared minus 2 times a times delta x. And at this point you plug and chug your numbers in. v120 equals the square root of v12f, which we just found was equal to 0, which we knew from the beginning rather, minus 2 times negative 8.33, the acceleration that we just found using the forces, times delta x, which is 17.4, which we were given at the very beginning of the problem. So you can plug all of this into your calculator, and you will find that v120 is equal to 17 meters per second. And that's going to help us because this is the velocity that the cars skid off with at some angle right after the collision. And let's draw a picture of that so that we can kind of picture and visualize how this is going to help us in solving the initial velocity from the whole collision. So here's our situation. Drawn it again. We have our car traveling southwest at 40 degrees. This was given, and our car traveling exactly to the east. And they collide, smack into each other, and they skid off at some other angle, which we don't know, at some velocity v120, which we actually do know. We just solved that. So we know that v120 is the hypotenuse of this triangle. So we know it's equal to the square root of v120x squared plus v120y squared. And we know furthermore that v120 is equal to 17. So we know that 17 is equal to the square root of v120x squared plus v120y squared. And I have one equation with two unknowns. I don't know v120x or v120y. But I do have a final condition and an initial condition. So I can use conservation of momentum, perhaps. And I have to remember that momentum is a vector, so I need to separate things out again into the x and y direction. So let's do the x direction first. And let's take this picture, and we're going to shrink this down and move it off into the corner so I can fit everything on here. So we have stuff going on in the x direction. We have some initial momentum and some final momentum in both the x direction and in the y direction. And I need to use these conditions to solve this. So initially, in the x direction, P0x has to be equal to P final in the x direction. P initial in the x direction is mass 1 times velocity 1 initial in the x direction plus mass 2 times velocity 2 initial in the x direction. So these are the two cars traveling at their respective velocities in the x direction. And that has to be equal to the final momentum, which is mass 1 plus mass 2, the masses after they crash together and combine, times v120 in the x direction. I have to keep vectors associated with vectors. I can only add things going in the same directions. So what I'm going to do, I'm going to solve this whole equation for v120x, because I can see that I have a v120x in my equation up here. So maybe I can start reducing some unknowns in my problem. So I solved this for v120x by dividing both sides by m1 plus m2. Divide both sides by m1 plus m2. My m1 plus m2's cancel, and I end up with v12x over here is equal to mass 1 times v10x plus mass 2 times v20x divided by mass 1 plus mass 2. And now I can plug and chug some things in. I know mass 1 is 900, so I plug in 900. Mass 1, 900. I know v10x is 14, because my first car is traveling entirely in the x direction at 14 meters per second. So v10x equals 14. Plus mass 2, which I know is equal to 1200. And then v20x I know is equal to v20 times the cosine of 40. And I can divide all of this through by mass 1 plus mass 2, which is going to be 2100. And that's going to be equal to my v120x. We can see something useful happening already. I'm getting v120x in terms of v20. And if we think ahead, I can do something similar in the y direction, get everything in terms of v20, and then I will reduce all my unknowns down to just 1. Let's keep going and see if we can do that. So I need to multiply these things out. If I multiply these things out, I get 900 times 14. And we'll simplify this a little bit, divided by 2100. So that's one part of my equation, plus 1200 times cosine of 40 times v20 all over 2100 equals v120x. And all I did here was rewrite from this line to this line, just to make things a little bit more transparent and clear about what we're doing. So I'm going to take this, I'm going to shrink this guy down, and move him. We're going to shrink this guy down. We're going to move these guys up here. And when you actually multiply all this out, this will become 6 plus 0.44 times v20. And that's what I get for v120x. Now let's turn to the y direction. In the y direction, I need to write down my momentums. So I have mass 1 times v1 initial in the y direction plus mass 2 times v2 initial in the y direction equals mass 1 plus mass 2, because they crash together and combined, times, make a little bit of space, v2 1, 2 initial in the y direction. So what can I do here is, can I cancel anything out? Well, I can get rid of mass 1 times v1y, because mass 1, remember, all the way up here in this tiny little picture up in the corner, mass 1 is traveling entirely in the x direction, so it has no y component. Mass 2 does have a y component. We have mass 2 times v2 initial times the sine of 40. You can rewind in the video to see where that comes from. And that's equal to mass 1 plus mass 2 times v2 1, 2 initial in the y direction. Again, we're solving this so that we can plug it right back in here. We can plug and chug some numbers in. Mass 2 is equal to 1200 times the sine of 40 times v20. We'll divide through by 2100 kilograms, following the same process that we did for the x direction. And that's going to give me my v120y. So v120y, when you plug all of this in your calculator, will give you 0.37 times v20. So I have these two equations. I've written the x and y directions in terms of just v20, the unknown that I'm looking for. And then I can pull back in this equation from the very, very first beginning part of the problem. And let's do that. Here's the equation that I have to work with. I can take this and I can get rid of the square root by squaring both sides. So I'm going to do that. 17 squared gives me 289. And that's going to be equal to v12x squared plus v12y squared. I can plug in my expressions that I found for v12x and v12y. v12x was 6 plus 0.44 times v20 squared plus v12y, which was 0.37 times v20 squared. I do the FOIL method on this guy, first outside, inside, last, and I end up with 289 is equal to 36 plus 5.28 times v20 plus 0.19 times v20 squared, and then plus 0.14 times v20 squared. I can combine like terms, so I can combine these v20 squareds, and I get 289 is equal to 36 plus 5.28 times v20, decimal right there, plus 0.33 times v20 squared. And then I can move this 289 over to the other side to get this into the quadratic equation form, where I have 0 is equal to negative 253 plus 5.28 times v20 plus 0.33 times v20 squared. And now to solve this equation, I need to use the quadratic formula, where I have a, b, and c. And let's see what that looks like. So let's do the quadratic formula. To find v20, we get negative b, which is going to be negative 5.28, plus or minus the square root of b squared, which is 5.28, quantity squared, minus 4 times a, which is 0.33, times c, which is negative 253, all divided by 2 times a, which is 0.33. Plug and chug these numbers in, v20, and you will find 21 meters per second. Or you will find negative 36 meters per second. And now we need to figure out which one of these, or if both of them, are a possible correct answer. Now we know in physics that the sign of an answer for a velocity tells you the direction that you're going. And if we go back in this video, and you go back in your solution and you look at what you assumed anything that was going to the right had a positive momentum. We also assumed that anything going down had a positive momentum. And after this collision occurs, we know that these two cars kind of skid off kind of to the right and going downwards. So going to the right, going down, that's got to be a positive velocity. If, on the other hand, the cars collided and they went backwards and kind of up, that would imply back and up, which would correspondingly be negative. So we would have the negative answer only if the cars somehow collided and ended up going backwards. And that's not a very physical, plausible situation. So we know that has to be only the positive 21 meters per second answer, because we assumed in our entire solution, you can go back and you can see it, that anything moving to the right gave positive, which we're used to, but we also assumed anything going down would be positive, which isn't quite as obvious until you go and you look back and see that we actually did make that assumption. So that is how you do this particular problem.